Okay. Before getting back to any physics stuff, oops, overshot. Tomorrow, next class, Friday, is the first midterm exam. 30 questions, multiple choice. Essentially all conceptual. You don't need a calculator. Just, it's all about thinking. I encourage you to take old exams. You'll learn the sort of questions I ask. You'll actually learn some of the questions I ask. They're similar to the homework questions. Very few quantitative answers. The quantitative answers usually have a name. The only numerical answer that I'm fond of is the number 0. It will show up periodically, but numbers like 3.6, no, they very, very rarely show up. Most quantities that show up, if they're quantities, they have a value like a force equal in amount to your weight, that kind of thing. Any questions about the exam? It's 50 minutes. Bring a pencil so you can erase stuff. I scan them myself, so it's not I can deal with pen actually. If you can use a pen, of course. If you make a mistake, we struggle, but we can deal with it. That's about it. You're okay with the exam concept? Actually, I will give you, the last thought is I will give you a little past 50 minutes, probably to 60 minutes. Don't stay too long. People do stay too long, and they suffer over questions they've already answered correctly, and they ruin them. People overthink questions. So if you know that's the kind of thing you do, learn when to stop. And being able to take the old exams allows you to figure that out. For example, I've encouraged some people to take the old exam like they would, just get it done, record your answers, and now go do your suffer over the answers trick. Spend another 10 minutes tearing your hair out over the questions that you're a little uncertain about, and see whether you improve your score or damage it. Okay? So that's all my advice for the exam. It will cover the material through today, and if I should finish at zero-graphic copiers, more or less. All right. Before going back to zero-graphic copiers, and thereby shortening the day, since an activity I'm involved in actually ended up on the virginia.edu homepage, I thought I'd take 2 seconds, yes, crazy things, 2 seconds to talk about that. Along with teaching, you're aware that faculty tend to do research. In fact, I could rant and rave about the balance between teaching and research, but I won't. But for the past long time, maybe 10 years I've been working on a strange material. I started as a rank amateur, and I ultimately became the expert in this material. The material that I started with was silly putty, and its relatives. So presumably you know about silly putty. How many know about silly putty? Okay, everybody knows about silly putty. Okay. It turns out it was misunderstood. It's 70 years old, give or take, basically. And it's been misunderstood ever since, and I'm now finally, I understand it, for better or worse. And because I understand it, it's like when you learn how to, if you're just following recipes when you're baking, you can't do anything except follow the recipes. Once I really figured out how to work with this material, it's like baking. Yeah, suddenly you can cook anything. You can make up your own recipes, and I can make up my own recipes. And I've made a material that has many of the characteristics of silly putty, but that is a solid. Silly putty is actually a liquid, meaning that if you subject it to certain stresses, it flows like a liquid. It changes shape and never comes back. I can make materials that change shape temporarily and then they come back. And we're about we're doing crowdfunding. We're doing a Kickstarter campaign at the end of this month for earplugs based on this material. And it's a shape memory material. What does that mean? It's almost something that we're defining as we create it. It's a material that has a fixed shape. It has a shape that it likes. And it will go back to that shape if you leave it alone. But you can temporarily take it out of shape, and it will learn a new shape and hold that shape temporarily. And then gradually go back. So in the case of earplugs, you can take this material, which it's a bulb. The earplug, we're called ear jellies at the moment. You can take, let's see if I can pull this off. Yes. it's got a bulb shape. So there's the bulb. And you can take it out of shape, and this one actually is, I'm in the world of prototypes. So this is a real one. Still a prototype, but at least it behaves the way it's supposed to. You can take it temporarily out of shape, put it in your ear, and it will try to go back to its original shape. And when it comes up against your ear canal, it'll stop, because it's actually an exquisitely soft material, but with a layer of shape memory on top. So you can take it out of shape. I'll just take it out of shape, just so you can see. There it's long and thin, and it'll go back to being a bulb gradually. And we can change the time scale over which that happens and so on. But when I say it's shape memory, it's very soft, but it has a layer of shape memory on top. What does that mean? So you can imagine this guy's going to go back. And the point is that it totally seals your ear. It presses very gently on your ear, and therefore it's super comfortable. And my buddy Rudy, who designed the earplugs and came up with the idea to do them, talks about the feel and the seal. It totally seals your ear, like against water, for example. And it feels like nothing. Like he describes waking up one morning and thinking he'd lost his hearing because he forgot he was wearing them. Anyway, so the idea of the shape memory is, so here you're looking at a shiny surface of a big piece of that same material, and it's in its favorite shape, and it likes that shape now. It's got a shape memory of this shape, and if you go wail on it with a hammer, you can take it just a little. I put a little bit of enough of a dent in it, you can just sort of see a little bit of dent. But if I push my finger, I can dent it a lot. So that it's a little tricky to get this to work out right. Let me take a nice shiny spot right there, and I can put my fingerprints in it. But it takes a little while. So there are my fingerprints in this material that you can hit with a hammer. What is that showing you? It's showing that when it's just left there in its favorite shape, and you hit it with a hammer, you're too fast. It likes its current shape. It won't change. But if you're patient, it will learn the new shape, even with very gentle force, like your fingerprints, like the ridges on your fingerprint will dent it out of shape. It'll learn the new shapes, and then it'll remember that shape for a while. It'll gradually forget it and go back to being flat. That big dent I put with my finger is getting shallower and shallower as we sit here. So the point with the earplugs is it custom fits to your ear. They do make custom fitted silicone earplugs, but they don't actually go into your ear canal because you can't get them in. They set aside. Yeah, Danya?
What differentiates it from other soundproofing?
What differentiates it from other soundproofing? It's because it's a silicone rubber, a solid silicone rubber. Once it's in your ear, it blocks sound pretty neutrally across the frequency spectrum and pitch. So it doesn't distort the sound the way a lot of earplugs do. So a lot of earplugs, the foam ones, for example, block certain range of frequencies more than others, and it skews the whole what you hear. So it makes conversation difficult, makes music bad, wrecks music. So it's like having a silicone rubber piece in your ear. Very, very little would distinguish its acoustic behavior from that of silicone rubber. But you can't get silicone rubber into your ear and have it sealed properly, because silicone rubber in general is too hard, has no shape memory. It's got a shape the whole time. You have to wedge it into your ear to get it there, and that's tough. So this you can custom fit it into your ear. It's insertable. Is that answering your question? Okay. Other questions? So it's a case where for forever I've done basic research in atomic molecular optical physics, little collections of atoms and stuff like that, all really in vacuum chambers and lasers and all that stuff. And I eventually got tired of doing that. I want to do something that actually has an impact on the world, not just like shows up in publications. So after a terribly long time, we're actually trying to put something out there that might help people conserve hearing. Just words to the wise. If you guys go to rock concerts and stuff like that, be careful. There's so many. I've talked to a remarkable number of people who have lost hearing at rock concerts. They come out and their ears are still ringing when they leave, and they're still ringing the next day, and it never quite recovers. So hearing protection. One of the quarterbacks from the Super Bowl, there was a picture of him with his daughter, with I think his daughter, with earmuffs on. Protection against sports noise. So these are real problems. Some huge fraction of people beyond a certain age have hearing damage and pain on hearing and all kinds of trouble. And we're hopefully we'll be helping that. Okay? Hey, so I'll stop. I'll bring this back to camera. No, not what I wanted either. That's what I wanted. I got it. Oh, and last thing related to that is that box over here on the left side of the room has, when I first started in this, I was literally working with silly putty and its related stuff. That's well, it was 50 pounds of silly putty. You're welcome to take as big a handful as you can hold if you can dig it out of there. It's tough to get out of there because it's a shape memory material too. It doesn't like to change shape quickly. You got to pull and be patient and get it apart. But it's one of my white elephants. I won't say walk away with the whole box, but take what you like and play with it. Okay? So that's my story about silly putty and it's viscoelastic silicone rubber here and these ear jellies. All right. It's on the front page of Virginia.edu right now, which is kind of whoa. Okay. Anyway, back to xerographic copiers. Change it. I used to do actually this semester. I used to walk through materials. One of the materials being plastics, the world of plastics and polymers, and would go through these things. And actually, I think I taught about how silly putty worked using the wrong understanding. That was like 15, 20 years ago. So but anyway, I could do the physics of these materials for real, but not right now. Okay, so back to xerographic copiers. And where I left off with things was the idea of an electric field. That you can think of the forces between two charges. Where are my little charges here? And I'm a little behind since the problem set dragged you through some of this already. These two charges, you can think of them as reaching across space and pushing directly on one another, pushing apart by way of Coulombs Law. Or you can think of them as creating structures around them in space known as electric fields, or the electric field, an electric field. And the electric field that lives around this charge, you can explore it by taking a tiny test charge. The concept is you take a test charge to find out what the field around this guy is like. And the only difference between a normal charge and a test charge is a test charge doesn't create its own electric field and therefore it's a conceptual idea, it doesn't exist. It doesn't influence the situation, it just observes, it's pure observer. So if you put the little test charge, let's pretend this guy's the test charge. Is that okay? I don't know. My hand will be the test charge. If I put it here, it's pushed away, because test charges are positive. It's pushed away, so the electric field here, it points away, and it's medium strength. You get it close, you come closer with the test charge, the force gets stronger, so the field is still away, but stronger than before. And you can sample it here, you can sample it in front of you, you can sample it behind you, the whole works. And here again, I encourage you to look at the video figure associated with this story in the book, because I'll let you see the field. Around a negative charge, it's a little peculiar, because a negative charge is a place test charges love to go. It's attractive to them. So the field around a negative charge, instead of pointing away from it, points toward it. And the field gets stronger as you get closer. Okay? Can you visualize the field approximately living around it? It is, as I said last time, it's a vector field, meaning that it has a value at each point in space. That's the field idea. And the value is a vector. It has a amount and a direction. So it's a nasty, complicated little guy, but it lives around these charges. And the reason that I bring it up is because it's real. It's not just a fiction that's just to make your life difficult. Electric fields are real. They have consequences. Their presence has consequences, and I can't leave them out. They're there. Okay, so you have this electric field that runs around a charge, and you can certainly figure it out in a simple situation where you have only one charge, and you want to find out what the electric field is around that. And I mean, you can think of got multiple charges around. You can think of them each having their own electric fields, But at any given point in space, you have to add all those individual electric fields to find out what's the grand electric field that would affect a test charge, because it's going to respond to all the fields at once, summed up. So I carelessly use the word the article that goes in front of electric field can be the, or I don't know. It's at any given location in space, you put a test charge there, it's only going to have one response. So it's dealing with an electric field that's due to everything else in the world around it. Okay, so do you want to say anything more there about that? Okay, so that's electric field. We're okay with that idea? How can you figure out the electric field at a given location based on what you know about what's around that location? Well, if there's only one charge nearby, you can figure it out kind of by playing with Coulombs Law and noticing what a test charge is going to experience based on Coulombs Law. You can sort of map out the field by considering its repulsion from this positive charge. But if the distribution of charges is really complicated, it gets tricky to figure out what the electric field is. If there are 3,133 charges around, you have to sort of figure out the electric field from each one and add them together, and it's a mess. So there turns out to be another way to figure out electric.
How are you supposed to calculate it if the test charges are just theoretical?
How are you supposed to calculate the electric field if the test charge is just theoretical? Because you put the hypothetical test charge there, and you can use Coulomb's law to figure out how much force it experiences per unit of its charge. If it's a 1 Coulomb little test charge, which makes it a huge test charge, it's going to experience a force you can calculate. So if you look at the force it experiences per unit of its charge, that actually is the measure of electric field. It's the force per charge. Force divided by charge. Is that okay? So you don't worry about how much charge it has. You look at, well, whatever the test charge has, 1 Coulomb, a trillionth of a Coulomb, you come up with the same electric field. The one with lots of charge experiences a big force. The one with little charge experiences a little force. It scales out perfectly. The force per charge is the same. Is that okay? I mean, it's good you asked the questions. I never even told you what the unit of electric field is. It's the force per charge. Okay, and in the SI units, that would be newtons per Coulomb. Okay, because Newton is the unit of force, Coulomb is the unit of charge. There's another way to look at the origin of an electric field, and it's the voltage gradient. First off, what's a gradient? A gradient is a continuous change in some physical quantity with location in space. For example, if we have, in the book, from blue to red, across a paint gradient, color gradient. You've seen color gradients, or if you've played around with any drawing programs, you can get color gradients all you like. So you can have pick any quantities that changes with location. There's a gradient then in that quantity, and the units are typically the quantity divided by a distance. Is that right? Yes. So voltage is a case in point. If the voltage near an accumulation of positive charge tends to be a very high positive number, and the voltage near an accumulation of negative charge tends to be a big negative number, minus 1,000 volts. So 1,000 volts here, minus 1,000 over here. Is that okay so far? And if you look between this, you're going from 1,000 volts plus here to minus 1,000 over there. That's a gradient in voltage because it doesn't just happen like go abruptly from 1,000 bang to, I don't know what the value is here, to bang minus 1,000. It sweeps across from plus 1,000 to minus 1,000. Because if you took a charge, a test charge, you pull it off the accumulation of negative charge where it loves to be, you'd have to shove it the whole way to get it over to the positive voltage. It hates being there. You have to do work on it. And if you stopped anywhere along the line, you would have invested only a fraction of the energy you put in. I mean, just to remind you what 1,000 volts means and a minus 1,000 volts mean, that's 1,000 joules per Coulomb of charge. So if you start over here with a Coulomb of charge at the location, where it was minus 1,000 volts. To carry that Coulomb charge from this place it loves to the place it hates, you're going to have to do 2,000 joules of work to move that Coulomb. It's 1,000 joules of work to get it away from the minus 1,000 volts to neutrality, to 0. And then you're going to have to do another 1,000 joules of work to get it over to the place where it's 1,000 volts positive. Because that's what 1,000 volts positive means, 1,000 joules per Coulomb. It's got 1,000 joules of stored energy, electrostatic, stored energy, potential energy. All right? But the whole process, the transfer process, didn't happen, it's continuous. You started at minus 1,000 volts, you carry this charge, and there may be some complexity to the work you're doing. It may not be completely uniform the whole trip, but if you stop halfway, you've put in half the energy. So at this point, that Coulomb charge is an environment where it's got no energy left. It's at 0 volts. It's not 0, yeah. You pulled it off the minus 1,000, you did 1,000 joules of work to get it up to here where it's no longer got, it's at 0 volts. 100 volts, 200 volts, 300 volts, and finally 1,000 volts. Is that okay? I mean, obviously very hand waving. This is the kind of thing to animate it would be nice, so you could visualize it more than just having me wave around. So, at every location in space, there's a voltage. And a Coulomb of charge there has a certain amount of energy in that Coulomb charge. And that means that there's this sweep of voltage, which we call a voltage gradient. And officially, gradients point in the direction of maximum increase in the physical quantity. So the voltage gradient here points from the negative 1,000 volt blob toward the positive 1,000 volt blob. And it's got an amount and a direction. The voltage gradient is how much the voltage changes per meter. And yeah, units of voltage, volts per meter. It turns out volts per meter is technically, it's the same units as newtons per coulomb. That voltage gradient is an electric field. Flipped in direction. It's minus the electric field, or minus the voltage gradient is the electric field. They point in opposite directions. The voltage gradient, because it officially points towards increasing voltage, points from low voltage to high voltage. The electric field points from high voltage to low voltage. They point in opposite directions. That's the only point here. But this voltage gradient is an electric field, meaning that if there are points along this trip in which the voltage changed especially quickly for some reason, those are points where in that short region of space, the voltage changed a lot. That means that if you move charge from the low voltage end of the region to the high voltage, you have to do a lot of work in a short distance. That's hard work there. That means you're pushing against a very strong something. That strong something is the electric field pointing the other way. So in regions where the voltage gradient is large, the electric field, because they're related, is large. And that's the key thing we need. You okay with the voltage gradient? Any questions about the voltage gradient? Any questions with the idea that the voltage gradient is associated with, is an electric field, although in the opposite direction? And that the regions of rapid change in voltage are the regions of strong electric field and hard pushes on test charges and any charges. Is that okay? All right. Yes, lots of hand waving here as I do this. So I want to bring up one more thing with this, and because I'm leaning towards to put this back into context. The reason I'm going through all this crazy harangue is because we're trying to figure out how the xerographic copier sprays electric charge onto the open face of its photoconducting surface. We'll learn how the photoconducting surface itself is allowed to conduct electricity when exposed to light. That's down on the road for us. Right now, we need to figure out how the xerographic copier decorates that open surface with charge. Then it will later erase that charge using light and then it will stick, by static electric effects, it will stick black toner or colored toner particles onto that open surface with charge, and eventually transfer that to paper and fuse it into the paper, and you're done. So really, the only two important pieces of complicated or foreign aspects of physics that we need in order to, in effect, mentally build a zero-graphic copier are the trick of applying the charge to the surface in the first place, and down the road, how you erase it with light. All right? So the spraying on that surface, you need to get the electric charge free into the air. And how do you get it free into the air? Well, you push it there. And you push it off of a metal by way of a very strong electric field right at the surface of the metal. So if their charge is inside the metal, bopping around, we know they will be on the outside of the metal. I mean, that we already know, because I showed you with this cup. Remember, if I put charge everywhere around that cup, the charge always goes to the outside because it can, and because that gets it as far away from its fellow light charges as possible. So there's no charge on the inside, it's all on the outside. What's left in a piece of metal for use in the zero-graphic copier is getting the charge to go to the surface of the metal and then jump off into open space onto the passing air molecules. And that requires a strong electric field. How do you get a strong electric field? Have a very fast change in voltage between on the surface and a smidge away from the surface. Okay, well, how in the world would you do that? The way you do that is make the surface small or thin. If you have a point or a very thin wire, we'll see the change in voltage is very rapid as you leave that surface and go out into the distance. And so that's where I'm going with this. And so here's the story I want to tell you. I started it about 5 minutes ago and on to other things back. If you have two surfaces, one 1,000 volts positive and one 1,000 volts negative, and they're identical, and they're sitting there facing each other like this. The positive voltage one, in all likelihood, has a lot of positive charges on its surface. That's where that's ultimately responsible for giving it a voltage of 1,000 volts. It will be uniformly 1,000 volts along that piece of metal, and how do I know that? It's because if the voltage, I'm going to leave the negative one. This is the positive sheet here. Suppose the top had a higher voltage than the bottom for some crazy reason, piece of metal. If that's true, then there's a voltage gradient in the metal because it's got higher voltage on the top than the bottom. There's a voltage gradient in between, which is an electric field, which means charge is going to be pushed, and it's going to move. And it will move until the voltage is the same. It's like water seeking its level. If you have a basin of water and you got high water on one side, low water on the other side, there is an altitude gradient in this thing. And it will move. An altitude gradient will give you forces here. It's a gravitational potential energy gradient, and the water will go to seek its level. The same thing happens in a metal. The voltage will seek its level too. You can't have a piece of metal sitting there with high voltage on one end, low voltage on the other. They hate it. It will move. Is that okay? If it's not followable, at least just understand that the voltage on that plate is all 1,000 volts. If current's running, if the charge is deliberately moving around, this is what I just said is not necessarily true. This is when the stuff's sitting there at equilibrium, no net force. Positive plate, all 1,000 volts. Negative plate, all negative 1,000 volts for the same reason. They're facing each other across empty space or air. If the plates are big and they're close enough together, it turns out the voltage goes very steadily. 1,000 volts, 900, 800, 700, 6, 5, 4, 3, 0, minus 100, minus 200, minus 300. It's smooth right across there, and dead center between the two plates is at 0 volts. And you can sort of figure this out by thinking about moving charges from the negative plate to the positive plate. You do work the whole way. It's dead steady work. You're doing the same amount of work every inch. And right in the middle, 0 volts. So far, so good? Let's get rid of the positive plate and replace it with a pin. Still 1,000 volts. It's a metal pin, 1,000 volts. And now the voltage sweeps from plus 1,000 to minus 1,000, but it's not uniform. If you're a bug sitting right in the middle between these two, looking left and right, you look left at that big negatively charged surface and you go, wow, I mean, you can hardly even tell how far away you are from it, you the bug. You get a little closer, it still looks like a big surface. It goes completely beyond your view. You can't really tell how far you are from it, right? Dominates. It's just a dominating surface. You look over there at the pin and you can hardly see it. Is it out there? You have to walk closer and closer until you're right up. Oh, there's the pin. So it has almost no influence on you when you're at any distance, and neither does its voltage. So sitting there in the middle between these two, the little pin and the big surface, the surface completely dominates the voltage. The voltage midway between them is not zero. It's pretty nearly the negative voltage of the negatively charged plate. Is that okay? It isn't until you get really super close to that pin, it starts coming up, it starts to look like the end of a ball, and it gets bigger and bigger. It's in that last millimeter, maybe, away from the pin, that all the change in voltage occurs, where finally it begins to have a serious influence on the voltage, and you go from minus 900, whoosh, up to plus 1,000. Wow, over a tiny distance. Big change in voltage over a very short distance. That's a huge voltage gradient. And associated with that huge voltage gradient is a huge electric field in the opposite direction. So big, it can push charge right out of that pin covered with positive charge out and out on the passing air molecules. And it does. You can also think of it as at the tip of the pin, it is decorated with positive charges. They are packed very tightly together on that pin, and they repel each other ferociously. So what I described up until the last 10 seconds was the electric field view of it based on voltage gradients. If you just go and look at the Coulomb view, which is just say, okay, you put a whole bunch of little positive charges all packed really tightly onto the turf of a pin tip. They hate it. They're pushing apart ferociously. They push so hard that one of them will go like, hey, goodbye, guys, I'm leaving. I'm going to jump on that passing air molecule and leave. And off it goes. So the air molecule now becomes a positively charged ion. Yeah?
How would it be referred to as a large voltage gradient if it's so short?
Why would it be referred to as a large voltage gradient if it's so short? Voltage gradient is the change in voltage per distance. So if the voltage changes by 1 volt over a meter, that's 1 unit of voltage gradient. But if it changes by 1 volt over half a meter, that's twice the gradient. And if it changes by 1 volt over a millionth of a meter, that's a pretty big voltage gradient, and therefore big electric field. Is that okay? So it's the big change in voltage over a tiny distance that creates the whopping voltage gradient. And so the charges jump onto passing air molecules. You might wonder why they don't just jump right out of the metal into the empty space. And they can. That's called field emission. It takes a bigger voltage gradient. The energy cost of having a charge, positive or negative, jump out into empty space is very big, particularly an electron, because you just want a free electron in nothing. That takes a lot of energy to get it freed up. It's easier for it to leave one object and jump onto another object because it polarizes the other object and sticks. That polarization effect applies even to molecules. So an electron sitting there by itself will love to stick to many atoms and molecules, effectively polarizing them and leaping on it. So that's a little oversimplification, so I should be a little careful. So the jumping onto passing air molecules it happens at a smaller voltage gradient / electric field. So it's the one that we care about. The field emission one is also interesting. It's used for various purposes, but it's another story. All right? So a thin wire, like a point, has the same effect. If you give it a large voltage, in the vicinity of things that are low voltage. So there really is there is a voltage gradient around. It will be very strong, particularly near the pin or the wire. If you just have a pin at 1,000 volts in the middle of nothing, it's the only thing around. It will dominate the voltage nearby because there's nothing else to affect voltage. So you need sort of the other surface out there to establish that the voltage has to change from the 1,000 volts on the pin to minus 1,000 on the surface. If that surface is completely missing that 1,000 volts on the pin, well, it's the only game in town, so it affects the voltage everywhere nearby, and you don't get the big voltage gradient. Okay, so what a zero-graphic copier does is it puts a large voltage, I don't know whether it's positive or negative, it depends on the copier, a large voltage on a thin wire. Pin isn't so useful, but a wire, what's called a corona wire, is the main story. And so all your zero-graphic copiers or laser printers, they have at least one of those wires inside. And sometimes you see this wire, depends on the model, and with time they become more and more invisible. Back in the old days, they were totally visible. You could see the corona wires. You often had to clean them, typically with a Q-tip. It would just be a little thin wire in there. Obviously, you unplugged the thing before you did this because it's going to be a high voltage when it's working. But you would go and you would wipe the crud off of it because since the wire is at a large voltage and is covered with one kind of charge, it will attract crud. It will polarize the dust that comes by, and the dust will go right onto the surface, and you will accumulate junk on it. So corona wires typically have to get cleaned periodically. For fundamental reasons, they attract junk. But having it, say, at high positive voltage means it will start spitting positive charges onto the passing air molecules. And now those air molecules, which are positive ions, just to give them a new name, will be attracted to anything that's got a negative charge or that polarizes nicely. And the photoconductor, if you recall, has on its back, I'll flip back to it just because I can. There. The photoconductor has metal on the back surface. Remember that? Connected in principle to the earth. So when you bring negative charge onto the open surface of the photoconductor, sprayed there out of the air, it attracts opposite charge out of the earth onto that metal backing. And now the charge that you just sprayed is happy as a clam to sit there staring across lovingly at the opposite charge on the metal on the other side of the photoconductor, unable to get together because it's in the dark. If you put light in there, they can get together and become history. They disappear. Okay? So to show you that this effect is real, I mean, I've done it already, bits and pieces, but let me just try it one more time here. So you can see the big spark happens when enough negative charge accumulates on the sphere to polarize this thing with positive charge. The electric field gets so huge because the voltage gradient is starting, the voltage gradient right now is 0. Now it's getting bigger and bigger, and as the voltage gradient gets bigger, the electric field gets bigger, and eventually the electric field is so big that it starts pushing charges and ripping apart atoms by way of collisions and catastrophes, and you get these brilliant sparks. So that's breaking down the air with a tremendous electric field. It just, I'm getting reboots over here. The computer's having fun. My monitors are going nuts. If I take a pin, right? This is a corona discharge right now. I am spraying positive charge through the air off that sharp point. It's a knitting needle that's been sharpened. You don't want to knit with this. It's shooting positive charge at the ball and canceling its negative charge. It can't accumulate any. So there's no lightning bolts. Boring. that okay? Convinced? So that sharp tip was being polarized by the negative charge on the ball. So positive charge was being pulled on this, coming out of me, coming out of the ground, actually. I was holding the dirty little secret. By holding this metal piece here, I'm actually connected electrically to the ground. So this thing was accumulating positive charge. The negative charge that corresponds to this positive charge, the negative charge was going the other way, being repelled as far away as possible. So it was off in Australia somewhere. All right? This is apropos of the question on the problem set about the pot that you polarize it by holding a candy wrapper up against it, and then you touch it briefly to the earth by way of the pipe, and now you're polarizing the pot-earth system. And I should actually answer this one because enough of you had questions about this, like what happened. If you have the pot, if I bring up a negatively charged thing, right? I can easily make this cover there. If I bring it up to the pot, it will polarize the pot, which is okay. The pot ends up with a positive charged side and a negatively charged side, which is okay. And then I take the negatively charged thing to get away, the polarization vanishes, and it's back to being neutral and evenly distributed charge, nothing special. But if I polarize it and then touch it to a pipe or something that connects to the whole earth, ding, I don't just polarize the pot anymore. I polarize the pot and the earth, the whole system. The positive charge ends up on this side near the wand. The negative charge goes as far away as it can, which is the other side of the earth. And to an extent, that's actually true. So it completely off across the globe. And if I bring the wand away before I detach it from the earth, nothing special happens. It goes back the way it was. But if I polarize the system and then, polarize the system and then break the connection, I trap the positive charge on the pot and the negative charge over in Australia. They can't get back together. And I have forever positive charge stuck on the pot. Questions about that idea? So back to this story. The negative charge accumulating on the big globe, the dome there, polarizes me and the earth. Positive charge gets pulled up onto the stick, onto the needle, and negative charge gets pushed away through me into the ground, into the earth, over to Australia. And positive charge then, because it's on the end of a needle there, creates a tremendous voltage gradient between the needle and a millimeter away from the needle, which is a huge electric field. The electric field is so big, it pushes charge right out of the tip of that needle onto air and sprays positively charged air ions onto the globe and cancels its negative charge. So no spark. That's the reason for the no spark. Questions about that idea? And the same thing's used in a xerographic copier. Thin wire, high positive voltage, or alternatively, large negative voltage. Either way, it'll spit negative charge instead of positive charge. That charge goes out into the air. It's attracted to things that can polarize or opposite charge. It sticks onto that surface of that photoconductor, decorates it uniformly, and that charge sits there until you erase it with light. Subsequently, then, you use this, what's called a charge image. It's a pattern of charge on that surface, once again in the dark, that can be used to attract toner particles. And they form now a visible pattern, the pattern of the document you want. The only thing that's left is to transfer it to the paper and fuse it into the paper, and that's all done with static electric tricks too. Okay? The last sort of public service announcement part of this is, I told you earlier Benjamin Franklin was sort of the premier scientist in the colonies of his era. He was really lots of stuff with electric charge. He's all about electricity. And he invented the lightning rod, along with all the kite flying and stuff. He used to, too many stories. What's the point of a lightning rod? So this is sort of a public service announcement, although it's 200 years too late. He was a big advocate of lightning rods. And here's the idea. If everybody in a town has a metal pin sticking up from their house, connected to the earth, as a cloud goes overhead with, say, negative charge on it, it will attract positive charge onto all those pins, which will begin spraying positive charge into the air and discharging the cloud. So it's not that the whole cloud will lose its charge. And it is possible, and it actually occurs. Yeah?
As a side note, Parisian women would like wear the lightning rods in their hat because like just France in general was so fond of Benjamin Franklin. So I latched onto that idea.
So Parisian women during Franklin's era would wear pins in their hat as lightning rods, mostly to advocate, out of their enthusiasm for Franklin. This that gives an extra interest to the second observation about this. You don't want to be the first person to have a lightning rod in your house, because one lightning rod won't successfully discharge the whole cloud, and it will attract a lightning bolt, because you will put this column of charge up there, sort of extending the height of your house and making it, saying, hit me, hit me, hit me. So the big problem was getting lots of people to adopt lightning rods. No one wanted to be first, because first is bad. 10th is fine. 10th's great. You don't want to be the only person walking around town with a pin sticking out of your head. Also, related word to the wise is if you're ever on a mountaintop on a day that's looking stormy and your hair starts to stand up, get down, leave now. Why do you think you're standing up? You're playing lightning rod, right? The charge overhead is pulling opposite charge onto you. It's causing repulsion. You're playing hair stand-up machine here. And if the gradient gets large enough, you're not going to discharge the cloud. You're going to have the cloud send you a lightning bolt, which you do not want to receive. Okay? So the lightning rods, they work nicely if the whole town adopts them. So everybody's got them. It's not that they are designated places for lightning to hit. They are, but that's not the main purpose. The main purpose is to actually stop the lightning itself by discharging the clouds for this very reason. Any other questions or observations? We'll call it a day. Friday, exam here.